This is a recording of a discussion about robotics between the following students: 1901 3256, 1900 3095, and 1900 8935. It covers the topics of making a line following robot that responds to barcodes to change its behavior, and overcoming a problem where the robot overshoots when trying to follow a line. We also briefly discuss robot odometry and calibration when trying to get the robot to turn. Additionally, we also talk about using object detection to create a robot that follows an object in its field of view.
Yeah, so we start off with typically with the line following. So there's a typical line following behavior or technique where it is to have the framework divided by 2 in order to find the center of the view of the camera. This is usually the referencing point to find the error between the robot's position and the line it's attempting to follow. The code uses frame width instead of the hard value, so that the center of the camera view can still be obtained even when a different camera is installed and used. So the intention is to get the robot to drive towards the line by finding the center of the line and then comparing it to the center of the camera's field of view. We'd accomplish this by calculating the number of black pixels seen in the line and dividing this by 2. This is then added to the location of the first pixel found. In order to calculate the error, we had to deduct half the frame width of the camera from the value of the pixel. This calculates how far away the camera is from the line. Usually this technique works fairly well as it follows the line directly, but occasionally an issue can crop up from time to time, such as an intersection of lines causing the robot to get confused or follow the wrong line. This is a problem for a robot utilizing standard line following techniques because the camera will begin picking up a direct line of black pixels across the width axis, which is basically left to right. So it basically gets confused between the line it's trying to follow and the width. This is where the Pix2 cam came into play, where instead of the Arduino doing the hard mathematics of the image itself, instead the Pixie 2 cam runs its separate functions and features to do the math and send it back basically. So after this, the Pixie cam simply returns the X-Factor data to the Arduino board so that the Arduino can respond with the appropriate and more correct behavior. This then, instead of following the line directly, attempts to follow the path set via the x-axis vector. The benefit of this is that the robot is much less likely to get confused when meeting an intersection of multiple lines.
Now we had a problem with line following, didn't we? Where as we increased the proportion value, the KP, to speed up the error correction of the robot, it overshot. What do we do to fix that?
Yeah, so there was a problem with the line following overshooting. It was creating a sort of hunting behavior. This is clearly not what we wanted, and so we modified the algorithm to create a type of buffering effect. This was then used to counteract the overshooting behavior. It does this basically by comparing the error by the previous error to result in a value known as the deriv. This value is used to create a dynamic change in correction speed. This basically means that as the robot gets closer to the line, the correction factor gets smaller and smaller to prevent the robot from overshooting the line. Yeah, so moving on to the discussion of rotation calibration, we had a task set out for that, didn't we, Jamie?
Yeah, we had to get the robot to respond to barcode inputs and apply turning behavior accordingly. But depending on the value of the barcode present, it would turn left or right. For example, if it saw barcode 1, it would turn left. And if it came across barcode 2, it would turn right. And we also needed the robot to turn on an angle of 90 degrees. But after multiple physical trials, we found out that the robot was only turning 72 degrees instead of the requested 90.
Okay.
The way we found this out is by marking out the turns using a protractor. Do you remember that, Cal?
Yeah. So we had to measure that, didn't we?
Yeah.
So what were the steps taken to resolve the problem then, after we found out it was only around about 72 degrees instead of a 90?
So once we marked it out and found out it wasn't actually turning, we compared the two of how much it actually turned and how much it was meant to turn.
Okay.
So once we had the correction factor applied and the robot was rotating accurately and correctly, we decided to explore some additional behaviors for the robot to exhibit, didn't we, Mike?
Yeah, I came up with something called I like to call the lost puppy, and it's essentially just a robot that will try and keep an object in its field of view and also stay in range. So as well as turning left and right, it would go forward and backwards. It behaves, well, it functions very similarly as towards the line following, that it tries to keep something to the center of its field of view. And as previously discussed, like the Arduino is not capable of processing the image data, but the Pixie Cam is capable of doing all of this. So Pixie Cam can identify groups of objects or groups of colors, blocks of color in its field of view, and it's able to identify them and save them as like an array or list of objects. It can be tuned to only focus on one color, and we chose to just focus on red. And the challenge was trying to get the robot to turn, first of all, to face the red object. As before, it's exactly the same logic as the line following. You compare the center of the object to the center of the field of view, and you create an error value and use this to drive the wheels to turn it towards the object. Then we moved on and thought, okay, so we want to make the robot now move forward and backwards, and how can we do this? Well, you can approximate a distance of an object by seeing how big it is in your field of view. So if an object has a fixed size, when it's close to the camera, it's going to appear bigger. When it's further from the camera, it's going to appear smaller. So we can simply just use the width of the image width of the object to approximate its distance. And now to do this, we actually had to explore the relationship between distance and width of the seen object. So what we did is we laid out a scale on the desk for distances, and we had a script running that would shout back print out the width of the object for the different distances. We recorded these widths and distances and then ran them through an Octave script that produced a graph. And this graph had a line through it which described the relationship of the width of the image, the width of the object in the image, and the distance. The gradient and the intercept of this graph were then used in the final algorithm. And then we applied a method, a function, where we obtained the width of the object from the PixieCam, passed this width into the method, and the method would reference the gradient of the graph that we'd explored and return back an approximated distance. And then instead of using the frame width over 2 as the desired track 2 for the object to turn left and right, we wanted to use a set distance. So we just keyed in a set distance and then said, right, when the object is too far away or too close, you're going to need to adjust your behavior. And it's exactly the same math. So instead of doing the center of the line minus frame width over 2, it's the distance of the object minus the distance threshold. And then you normalize that by dividing it by the distance threshold, and then that's used as a coefficient to multiply it against the speed to track to and from the object.
When you was doing that, what was the biggest problem with doing that, do you reckon?
I wouldn't say it was a massive issue, but it exhibited the same behaviors as with the line following, considering the fact that it ran on the basic same logic. It had the same hunting issue. Although, interestingly enough, it only happened when it was driving to and forward the object, not turning left and right. And it would occasionally get stuck in a loop of driving forward and backwards. We could have fixed this by either having a conditional statement where it would only try to move towards or from the object if the error was high enough, or we could have used the same approach as applying a deriv to slow the robot the closer it got to the object.
Okay.